Hello everyone, we're back, and as you might realize, my hair is a bit different. Well, time passes. We were still talking about capillarity. So back to our first slide. Do you remember how we should interpret water table fluctuations after the concepts we just learned? So that's the idea. We've seen the concepts, and now we have to think about how we're going to use those effects. Actually, those effects are quite interesting, but not that obvious when we're thinking about the use in a real field situation. Well, first thing is, when the water table rises, water, the wetting phase displaces free phase, non-wetting phase, upwards. Yes, we're talking here about a DNAPL. So, when the water table moves upwards, we have here, can you see here? We have the LNAPL here. So, as the water table raises, it brings the LNAPL with it. But the water here and the LNAPL here, we have a contact, an immiscible contact. This is the point. Not only we have water here and the LNAPL here, but we also have the porous medium that makes all the difference. Porous medium is what makes the difference. That's why we hydrogeologists and reservoir engineers and people like that use that information, because the porous medium makes a difference. So again, as the water table is rising, right, as it's going up, it tends as wetting fluid to follow the smaller pores first, as we mentioned, right? So water goes upwards and it displaces the free phase. Well, when the water table lowers, right? The water table lowers, free phase displaces the water, or more generally speaking, non-wetting phase displaces the wetting phase. Okay, so we have two different movements. Here we have wetting phase displacing the non-wetting phase, and here we have non-wetting phase displacing the wetting phase. Well, when we're thinking about that situation, things are a bit interesting. Look at that. Here is that the situation where the water table is actually moving upwards, right? And it is actually, look, this is the water, clean water. This is the residual zone, the smeared zone, where the free phase has become residual phase. And here is the LNAPL itself, okay? So, as the water table raises, we have a process that's called imbibition. The process is called imbibition, when the wetting phase displaces the non-wetting phase. On the other hand, when the water table is moving downwards, right? So what happens is that the free phase is actually his name is non-wetting phase. The free phase in this case is displacing the wetting phase, and that new situation is called drainage. So drainage and imbibition tells us, these names, they tell us where the water is moving, if it's being displaced by the non-wetting phase, or if it's displacing the non-wetting phase. If the wetting phase displaces the non-wetting phase, imbibition. If the non-wetting phase displaces the wetting phase, it's called drainage. Okay? Well, We'll come then to the simplest pore structure that we have. And I'll have to make here some explanations for you again. So we'll make sure you know what's going on. When we're talking about that pore doublet, we'll have to think about the simplest structure that we have. Think about a capillary tube. Here I have a capillary tube. Can you see that? I see the capillary tube here. Well, a typical capillary tube is a linear tube. But in that situation we have a special tube, not a single capillary tube. We have a capillary tube that splits in two. It splits in two and has one way upward and one way downward. Two ways. You see? It has two ways. Okay, so the water comes here. Okay, yeah, putting the finger behind, you don't see it. Well, when the water comes here, it has a possibility of moving to this direction or to this direction. And it's the same for the wetting fluid as it is for the non-wetting fluid. And we're going to study and try to understand what happens in the simplest pore structure. Why? Because it's going to tell us exactly how the phenomenon occurs. This phenomenon of capillarity is very important, and it defines how free phase and residual phase behave. So please pay attention. In this simplest pore structure, as we have here, I can show you, we have here one dark fluid, and we have a clear fluid or white fluid here filling all the pores. Okay, so I have one capillary size tubing that splits in two and then merges again here. So here and here. If you pay a close look to this guy, if you pay good attention, you will realize that the upper portion is slightly smaller than the lower portion of the tubing. Okay, take a look again. You can compare to the size of the circle that I'm using. Look again, it's smaller. So when I'm talking about something that's smaller, you have to remember that we're talking about the capillary forces, and capillary forces are inversely proportional to the size or to the radius of the tubing. Well, if it is inversely proportional, the smaller the tubing, the larger the capillary force, right? The larger the tube, the smaller the capillary force. Okay, back to our pore doublet then. Well, as you learned already, if you take a look at this meniscus here, look, or this one here, you may say with total safety that this guy here, the dark fluid, is the non-wetting fluid, and the white fluid is the wetting fluid. Why? Because the fluids are such that the fluid that is on the concave side, right? Concave side is always the wetting fluid. No, sorry. The fluid that is on the concave side is always the non-wetting fluid. And the fluid that's on the convex side is the wetting fluid. So we take a look back. This guy here, the black, is on the concave side. So it is called the non-wetting fluid. And the white guy is the wetting fluid. Well, we use the meniscus because meniscus usually is simpler to understand or to visualize than using the angle here. I could draw an angle and see that the smaller than 90 degrees angle here is in this guy in the water here, this guy. in this situation has the higher density by definition, and we will have concluded that this white is the wetting fluid as well. But the meniscus will do the same job for us on a more straightforward way. Okay? Again, so now we will see that as the fluid is moving, it'll have to take a decision to which pore is going to go. Let's see then. Well, we'll have a pore doublet here for you, and you may take a close look and you see there is a red thing here, all blue, and there's a red thing here. Okay, well, this red by the meniscus, we may comfortably say that this guy here is wetting fluid, and the blue is going to be the non-wetting fluid. All right? Well, then by imbibition is when the wetting fluid displaces the non-wetting fluid. Let's take a look. Wetting fluid is displacing. Look, it's moving, and you'll have to pick one side. Oops, first on the top. Oh, now at the bottom. Why? What's going on? Again? Sure. Look at that. It stops a little bit here. It slowers the movement a lot. And then it moves ahead. It keeps going until it touches here. Touch down. Oops. Faster at the top portion, then slower at the bottom portion. They coalesce and they move together. Okay, I'm gonna explain that to you and then repeat again. I know you like to see that over and over again. Okay, when this fluid, the red fluid or the wetting fluid is invading here, when it reaches this point here, you see on the movie that what happens here? Here you have one radius, right? And as it comes here, the radius of the meniscus increases. Well, since this fluid wants to invade, it's acting as creating a capillary force to displace the non-wetting fluid. But as the capillary force gets weaker, why? Because the radius got bigger. As the radius increased, the capillary force decreased. So it moves slower to reach this point here. At the moment that the new large meniscus touches this guy here, oops, sorry. At the moment this meniscus touches this guy here, it actually flows faster through the top portion. Why? Because the radius here is larger. Sorry, is smaller. And the smaller pores favors the movement of the wetting fluid. You see that as this is moving, the larger radius here gets to a halt. It stops here. It doesn't move anymore. Until a given point where this meniscus here gets larger. Large to a point that it gets even larger than this one here. And this starts to flow. Because it always picks the smaller pore first. So it moves to this side and then it coalesces and goes to this direction. Okay? That's the explanation I'll have to. I'm just moving back the slide because I click it wrongly. Again, take a look at the movie. Large pore or large radius, smaller capillary force. very large radius, very small capillary force. It touches, follows here. And now this guy moves because this radius gets larger than this one here. They coalesce and go together. Once again, now I'll shut up. Okay, you guys can go back and forth as many times as you wish. Why? Because you can take a look at the movie, please. You have this good resource of the video. You can flip back a bit, see how it moves, and then understand all that. This is a very, very good little movie that makes you understand why the fluids follow that path by just attending the Young's equation. Okay? That's very, very obvious now that you have the information. Okay, now we go to the drainage. And again, you may see that we have a little blue fluid sneaking in here. Okay? Well, this fluid now is going to displace the wetting fluid. It's a drainage. It's a non-wetting displacing wetting fluid. Well, but if the blue fluid is the non-wetting, it is likely flow, or it has to flow through the larger pore. Let's see how it goes, and then we talk. Whoops. Uh-oh. Again, that's a bit weird, isn't it? Oops. Uh-oh. Yeah, it is weird, isn't it? This guy stayed behind. So we left wetting fluid behind. This is called irreducible water. Don't call this residual phase, because residual, we tend to save this terminology for non-wetting fluids, okay? That gives us an idea of a contaminant source when we talk about residual phase. So this is irreducible water. Let's do that again. And the question is, why it stays here and here? Look, answer is going to be again on the size of the pore. Well, you have to assume that for the non-wetting phase to drain the wetting phase, right, you have to have an external force that pushes it to the pore, right? Just like when we have the water table lowering. So we have gravity bringing the free phase down. Okay? Well, as it enters here, you have a meniscus, and the meniscus gets larger. And as you know, the capillary pressure is acting from right to left. It's against the movement. Well, as the meniscus get larger, the capillary force gets weaker, right? And then, well, to a point that it's easier for this fluid to invade. And then it touches here. When it touches here, again, it's going to split into a small radius here, into a larger radius here. And as capillary forces acts in that direction, from right to left here, from right to left here, this guy will suffer. This blue fluid, the non-wetting fluid, is going to suffer a much higher pressure against its movement on the top portion. So it's easier to move through the bottom portion, and it goes through the bottom portion. As it reaches here, differently than what we had there, the radius is still big, and it keeps bigger and bigger, and it leaves this guy behind. It just snaps off from the continuity that we have for this wetting fluid, and it leaves the irreducible water behind. Let's see that again. Larger pore, bigger, look. Meniscus never gets smaller here, so this would move. It's always bigger, and it leaves this behind. Again, this is very important, and it is very important that you take a close look. Take a look at the movie I showed you and see how that works. You have to see that over and over again. I know some movies are much more fun than that, but good intellectual understanding gives you pleasure as well. So take a close look and you understand what happens. In our next class, we're gonna make this even more complex, and then you'll have more fun. Take care.